Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton and I am the RASC DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with our outreach coordinator, Quinton Wayrich, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us make sure that all our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are happy to bring you virtual programming this summer instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. Tonight, it's my great pleasure to introduce our speaker, Dr. Jess McIver. Dr. McIver is an assistant professor in the Department of Physics and Astronomy at the University of British Columbia, and she's the Canada Research Chair in Gravitational Wave Astrophysics. She leads the UBC Gravitational Wave Astrophysics Group, the UBC LIGO Group, and the UBC Triumph LISA Group. She specializes in characterization of the advanced LIGO detectors and astrophysical gravitational wave data analysis. Wow. Tonight, Dr. McIver's lecture is titled, "What Can We Learn from Gravitational Waves?" It examines where gravitational waves come from, how we measure them, and what they can teach us about the universe. If you have questions for our speaker, please do post them in the YouTube chat. Dr. McIver will have time to take questions at the end of her talk. Please join me now in welcoming our guest for tonight, Dr. Jess McIver.
Hi, everyone. Good evening. So my name is Jess McIver. My pronouns are she, her. I'm joining you from sunny Vancouver, from the traditional unceded territories of the Musqueam people, and I'm really delighted to be able to tell you about gravitational waves. So let's start with light. So we've learned pretty much everything we know about the universe with electromagnetic radiation. Through telescopes, through satellites, we have learned about the structure of our own galaxy, about distant galaxies, the expansion of the universe, dark matter and dark energy. We've learned all of this with data from electromagnetic radiation. But light does have some downsides. So for example, it's really tough to see past other light. So for most wavelengths, it's really difficult, if not impossible, to observe during the daytime. We also see that light is very strongly interacting, which means it gets blocked or distorted by matter, including dust, as it travels really vast distances to Earth. So June, near the summer solstice, is a really neat time to be talking about other messengers, including gravitational waves. So as we go through these very, very short nights, let's think about what we can learn about what's out there in the dark. And this brings us to gravitational waves. So these are very weakly interacting, tiny ripples on the fabric of space-time itself. And what that means is that it's going to make them really, really hard to detect. So we'll see that a little bit later on, how we do that. But it also means that they're going to propagate for enormous distances and give us this crystal clear signature of the dynamics that produce those gravitational waves. So they're going to pass through galaxies, through the Earth. We can see them any time of day or night. And they're going to give us this glimpse into this dark aspect of the universe. What's out there moving around in the universe? So we're going to learn about gravitational waves. And in order to get an intuition for what they are, let's start with waves generally. So here's something that's pretty familiar. So waves in water, especially if you are like me, living near a body of water, we can get the sense that waves are energy that's moving through some medium. So waves are going to have an amplitude, and if they're like water waves or like gravitational waves, they're going to that amplitude is going to pass through that medium like water, or as we'll see, like space-time. But I also want to mention that we do have this intuition for waves coming in other forms as well. So what you're about to see is a time lapse, not of water this time, but actually of clouds. So let's take a look. So here now we've got these photographs taken over some minutes, so spanning minutes that we're seeing these clouds beating up against the shore of this mountain. So waves are a really natural phenomenon, and it's not just water where we see them. We see them in many, many different places. And as we're going to see, one of the places that we do see them is space-time itself. So we're going to learn everything that we need to know about general relativity to understand gravitational waves. So the equation that you see on the left-hand side here, what that's telling you is that the distribution of matter and energy is going to dictate the curvature of space-time, and how space-time is curved is going to dictate how that matter is moving through space-time. So let's take a look here. So this green grid, so this is the fabric of space-time. And if I introduce some massive body into this fabric, what this is going to do is it's actually going to introduce this curvature. And if I have some smaller body, let's say I have a planet like the Earth, and I introduce that into an area that has a star nearby, this planet is going to experience gravity, this force that we feel pulling us down to the Earth, or the Earth feels pulling towards the sun. So this is actually an artifact of the Earth trying to move in a straight line through this curved space-time. So this is what gravity actually is at its heart in this general relativistic framework. And if we introduce motion, so just like if I throw a rock into a pond, if I have some motion in space-time, this is actually going to propagate, ripple across the surface of the pond, or in my case, this green grid of space-time, like a wave. So let's first get into what else general relativity predicts. So how do we know that this is true before we even think about waves in space-time? So if this is true, we expect to see that light is going to bend around this curvature. So this is one of the key predictions of general relativity, is that space-time curvature should bend light. And this was actually proven about 100 years ago. So Eddington was the first to get credit for this observation. There's also a Canadian expedition a few years later that confirmed this. But let's take a look and see how this works. So let's say we're here on Earth, and we have a really good sense of where the stars are in the sky. And let's say we have some nearby star, nearby relative to the background of very, very distant stars and galaxies. If we've got some massive body like the sun that we can use to test this deflection path, what we're going to do is we're going to look for something to block the light coming from the sun, so that we can check and see if the sun itself is actually bending light's path. So here's an example. So here's the actual position of a distant star. So the distant star, it's going to have light that's bent. So as it encounters curved space-time near the sun, it's going to be bent so that it appears to be in a different location in the sky. And this is how Eddington and that team first observed this well over 100 years ago now. So we've had evidence for general relativity for a very long time. And another one of the most well-known predictions is, of course, black holes. So this is some object that's so infinitely dense that the curvature of space-time is essentially infinite. And what that means is that light is bent so much that it can't escape at all. So we've got what's called this event horizon, so beyond which point nothing, not even light, can escape. And this comes from this infinite curvature of space-time. And we do actually have a lot of evidence for black holes as well. So some of that is from light. So this is an illustration of a black hole with a companion star. And the black hole is slowly tearing matter off of this companion star. This is forming an accretion disk and accelerating matter into two jets that are blasting away from this black hole. And astronomers that use electromagnetic radiation, or X-rays in particular in this case, can actually see both the companion star and also that black hole signature, the X-rays coming from that black hole. So we're actually able to get an estimate using light of some black hole masses. And we'll take another look at that a little bit later on. And you may also remember this being in the news. So this is the first image from the Event Horizon Telescope. So this is a network of essentially an Earth-scale radio telescope with radio telescopes from all over the world that combine their data and stitch them together in this image. And we're looking at essentially this shadow in the center. So this is where the event horizon would be, and the signature of this glowing gas around the outside of this black hole. So this is a really powerful technique. You may also remember seeing in the news not even a month ago that the same team has now made an image of the black hole at the center of our own galaxy. But there are some limitations to this technique as well. So we've got this limited size of the surface of the Earth, and this is essentially going to make an object that's about as big as the diameter of the Earth itself. And what this means is that we can focus on objects that are about so big and about so far away. So there are really only maybe a handful of black holes that we're going to be able to use this technique for. So we're going to need to look for something else to tell us about black holes, especially black holes that don't have gas or companion stars around them to give off this light. So what can we do? So we can use this other prediction from general relativity, that where you're introducing this motion within space-time, this is going to give us waves, just like the surface of a pond. And we actually saw evidence for this effect really early on as well. So what you're looking at here in this graph, so each one of these red dots, this is the measured period of two neutron stars that are orbiting each other. And general relativity says that two compact objects like neutron stars or like black holes, as they're orbiting each other, they're radiating away energy in the form of gravitational waves. And what that should do is spin that orbit up so that they get closer and closer together, and that period gets smaller and smaller until eventually they merge. And each one of these red dots is showing us that that is indeed the case. So measured over decades, you can see this pulsar. So this is the Hulse-Taylor binary pulsar that won the Nobel Prize in 1993. Does follow this prediction from general relativity very, very well. So let's take a look at what we see here. So in this case, so we have this pulsar. So this is a neutron star with a really strong magnetic field. So this is giving us a signature that's pulsing in time every time that this beam of radiation is striking the Earth. And we can use this light, this electromagnetic radiation, to measure how far apart these neutron stars are until eventually, as we expect, they're going to merge. And this is going to take such a long time that we don't have the millions and millions of years to observe this phenomenon with light. So this is a simulation. We're going to need to directly observe these gravitational waves in order to see this effect. So let's pretend we had powerful enough telescopes to see this and we got really lucky. So let's say we've got perfect optical telescopes and we could see these two black holes in a dense stellar field. This is essentially what we would see for two black holes roughly 30 times the mass of our sun. They're going to be orbiting each other closer and closer together until eventually they merge, and then that final black hole is going to ring down like a bell. So let's take another look at that. Let's back this video up and watch this again. So watch this warping of the star field around these two black holes, this breathing of space-time. So these are the gravitational waves that are propagating out at the speed of light that are telling us about how quickly these two black holes are orbiting each other. And we can also see this jiggling around of space-time as that final black hole rings down like jello. So let's see what this looks like. Let's say we don't have perfect telescopes, which we don't expect to have telescopes that crisp and that are going to be able to make those observations. So we're going to need to look at gravitational waves. So let's take those same two black holes, and now here we're going to be looking at space-time. So let's take a look. So the colors here are telling us about the curvature of space-time and how much that space-time is warping. So we've got here again two black holes, roughly about 30 times the mass of our own sun. And now what you're seeing on the bottom here, so this is actually tracing out the signature of the gravitational wave that will be produced by these two black holes. And this is a really powerful way for us to predict, using general relativity, what that gravitational wave signal should be. And this is capturing so much information. You can see these black holes that are spinning up faster and faster. The amplitude of the signal is increasing more and more until it spikes. So it's going to reach this peak amplitude just as these two black holes are about to merge into this final larger black hole. And this gravitational wave signature capturing all of these dynamics that are happening completely without light. This is going to be propagating off at the speed of light. And if we built an interferometer to capture the signal, we would be able to read out exactly what those black holes were doing at the time that they merged. So what does this look like in practice? So let's say we've got a gravitational wave that's passing through the Earth. So if it's coming into or out of the Earth, just like it's coming into or out of the plane of the screen, what that's going to do if a gravitational wave is entering this square is it's going to be stretched and squeezed in two different directions. So this is telling us that as one direction is stretching, this other direction is being squeezed and vice versa. So I've sort of got this orthogonal stretching and squeezing pattern that's telling me about the shape, the signature of whatever it was that made this signal at this particular frequency. So this is the same time series that we were looking at the last slide. This is telling us about the amplitude of the gravitational wave over time. And this is going to be stretching and squeezing space-time as it's passing. And we can leverage this, what we know about what gravitational waves should do, to build our detectors. So we're going to choose to sense in these two perpendicular directions when we're building these great big, enormous detectors. So let's look at how this works. So we're going to take some coherent laser light and we're going to use it like a timer. So we really want coherent laser light like you'd see with a laser pointer, because we're going to get these very nice regular wavefronts. And we're going to use that as a timer to test how long the light takes to travel in two orthogonal directions. So we send this laser light down to what we call a beam splitter. So this splits the light in those two orthogonal directions. And if there's no gravitational wave, then it's going to take this light exactly the same amount of time to bounce off of this mirror, which is 4 kilometers away for the LIGO detectors. And it's going to take the light in this arm exactly the same amount of time as it will for this arm to travel all the way down 4 kilometers and back. And when this light is recombined, I don't expect to see anything at my output photodiode. So I offset this light just a little bit so that it cancels itself out. But if I introduce a gravitational wave into my detector, now I'm going to get this relative stretching and squeezing, and I'm going to get this very small difference in the time of arrival of the light. This is going to make an interference pattern, and it's going to allow me to read directly what the time series of that gravitational wave is. And then here's some example data from the very first detection of gravitational waves with LIGO. And we have a whole global network of these observatories. So we have these 2 LIGO detectors in the US. So again, these are 4-kilometer long arms in 2 different directions. So one here is very close to where I am in the Pacific Northwest, in a desert, so on the other side of the mountains from where I am. and the other is in the swamp in Louisiana. And then we also have our sister detector, Virgo. So Virgo is 3 kilometers long and in Italy. And all three of these detectors that participated in the previous observing run, so this ran from April 2019 to March 2020, they all have the same basic shape. We've got some input coherent laser light. It splits and cycled in kilometer scale orthogonal arms. And then when it's recombined, we're able to read out that gravitational wave signature. And what's really exciting looking ahead is that we've got another detector coming online in Japan called Kagra. We expect a fifth one, a third LIGO detector in India that'll bring us up to 5 sometime in the middle of this decade. So that's going to be really powerful in observing gravitational waves. Well, let's get a closer look at the LIGO detectors. These are, again, 4 kilometer long arms that you're seeing here. So these are the concrete tubes that house this vacuum enclosure that's 8 kilometers long continuously. So it's one of the longest vacuum enclosures in the world, second to CERN. And here you can see some of our scientists and researchers in the control rooms adjusting the optics and getting us ready for an observing run. So this is what the folks who are at the sites are working on right now, is preparing us and upgrading those detectors for the next observing run. So let's put this all together and see what we actually get with all of this technology. So these really, really long arms and these this complicated optical structure. So how sensitive does that make the detectors? So we're going to see that to scale here. So we're going to start by zooming around with the electron outside of a hydrogen atom, and we're going to zoom all the way down to the surface of the proton, and we're going to see to scale the relative distance measurement sensitivity that the LIGO detectors have. So this is about 10,000 times smaller than the diameter of a proton. That's the precision that the LIGO detectors are operating with. And I'll also mention that this graphic was made in 2015 at the time of the first discovery, and we're actually doing about a factor of 2 better than that now. So let's see all together end to end the full picture. So we've got these 2 black holes. They're emitting gravitational waves. That gravitational wave signature from those emerger is going to travel off at the speed of light. So it can travel for billions of light years before it reaches the Earth, which was the case for the first detection. And then what happens when it reaches the Earth? So I'm going to advertise here that we call this the Jello Earth for reasons that will become obvious momentarily. So this is vastly exaggerated. This is not to scale. So again, these are tiny, tiny, tiny fractions of a proton is the kind of scale that we'll see. But let's say we have a gravitational wave that's passing through the Earth, that's going into the plane of the detectors. This is what we'll see in that laser light. So we're actually going to be able to capture the signature of those 2 black holes in our interferometer directly. So let's take a listen to what this data actually sounds like. So I'm about to play you a clip of real gravitational wave data. So this is from the 2 LIGO detectors in the US. And what we're going to see, so this is time on the x-axis down here, and then frequency. So this is a way of visualizing how quickly those 2 black holes are spiraling together before they merge, where again, we expect this to be sweeping upwards as they're getting closer and closer together. So let's take a listen and let's hear what this real data from LIGO sounds like. So this is the sound of black holes. And this is, again, just directly taking that time series data. So sort of using the LIGO interferometers, sort of like a radio, to capture the sounds of space-time, and then turning that into an MP3 file that we can actually hear. And this is unique to ground-based detectors, where the range of the data that we're taking is actually pretty close to the range of human hearing. So we can translate this and use our brains as really powerful signal processing to actually hear directly the sounds that space-time is making with these dark objects that are crashing together in really, really vast distances. So we also can tell from the signature what those two black holes were. So how big were they? How big were each one of them? And roughly about how far away they were. And this is really unique in astronomy. So distance is really, really tough to tell when you're using light, but gravitational waves are going to give us this direct distance estimate that comes from understanding general relativity. So let's take a look at this. So here I've got time and then the amplitude of my gravitational wave signal. And I've got some model for my data, that's this gold line here. And then I've got some real data that's here in blue. So what's going to happen is I'm going to evolve my model in mass, and then I'm going to try and match up that model in phase with my data. And this is giving me a good match between my model and my data in mass. And then general relativity tells me, okay, well, if it has this total mass, so if the two black holes were roughly about so big when they merged together, that tells me what the amplitude should be. And if I know what the amplitude should be, I can look at the amplitude that's in my data and infer the distance. So let's take a look. So I am evolving my model in mass. I'm looking again for this match in phase and how well these wiggles are lining up between my model and my data. And then I'm just going to scale this directly to the amplitude that I see in my data. And now I've got this direct measurement of distance, which is going to be a really powerful tool in astronomy to get this distance measurement. And I can also tell if I've got more than one detector, and soon we'll have 5 of them around the world, but if I've got more than one detector online, I can use this to triangulate where in the sky the signal's coming from. So let's take a look at this. So this is the very first detection of neutron stars merging with gravitational waves. So we were looking at data from the very first detection of 2 black holes crashing together. This is from a neutron star merger. And what you're looking at here are the sky localization maps from gamma ray satellites. So we've got this 2-dimensional sky map from Fermi and this timing ring from Fermi and Integral, the relative time of arrival between those 2 satellites. And this double banana that you're seeing here in green, so this comes just from the 2 LIGO detectors. And you can see that there's a region of overlap we have here. And now I'll show you how powerful it is to add this 3rd detector. So this is what happens when we add the time of arrival from this 3rd detector. So this is Virgo. And again, let's remember that we're also getting distance. So this is a 3-dimensional sky map that astronomers can use to identify host galaxies inside it and use that to search for these electromagnetic counterparts. And this is indeed the host galaxy for this very first multi-messenger discovery with gravitational waves. So this is NGC 4993. So let's take a look at those images. So these are the discovery images of the optical counterpart to this gravitational wave signal, where we saw in gravitational waves how those 2 neutron stars tore each other apart and crashed together. And then now we're seeing the afterglow of the kilonova, which has all of this rich information about the formation of heavy elements that has actually shifted our thinking about how heavy elements like gold and like platinum are formed in the universe. So instead of thinking that supernovae are really the dominant driver, now we think it's actually neutron stars that are crashing together and forming these heavy elements. So if you are in the market for a task to do, if you've got a telescope in your backyard, LIGO Virgo alerts are a really neat thing to keep track of. So all of those alerts are public with the sky map and the distance. If you're interested in helping us out and looking for some of these kilonova counterparts. But let's take a look at all of the rich wealth of information that these kinds of events are telling us. So here we've got 2 neutron stars, and this is where we're seeing the signal in gravitational waves. So we're looking at the dynamics of those 2 neutron stars as they're orbiting closer and closer together until they tear each other apart and they merge. And then a flash of light in well, first in gamma rays, we get this gamma ray emitted signal, but we actually over time see this signal evolving around across all these different wavelengths. So we see X-rays, we see it in also optical lights, and then eventually this radio afterglow. And this has just a wealth of information about these objects and what they're producing in terms of heavy elements that then gets spread out into the universe. And it's not just these 2 discoveries that we've made with gravitational waves. So we're now looking at this vast stellar graveyard that LIGO and Virgo have revealed. So let me walk you through what we're looking here. So the y-axis here is the mass of each one of these dots. So each dot is some kind of a stellar remnant, a dead star, and its masses and solar masses. And the x-axis doesn't really have any meaning. It's just getting tough to fit all of these dots onto one plot, which is a nice problem to have. But each one of the yellow dots, so these are neutron stars, maybe pulsars, with a mass that's estimated with electromagnetic radiation. And then each one of the red dots, so this is a black hole with a mass that's estimated with electromagnetic radiation, so usually an X-ray binary, like we talked about. Each one of the orange dots, so this is a neutron star with a mass estimated with gravitational waves. And each one of the blue dots is a black hole with a mass estimated with gravitational waves. And you might notice that each one of these events, so every time we observe a gravitational wave, we get 3 measurements. So the 2 component objects and then the object that they merge into. So they always come in 3s. And you might also notice that gravitational waves have really unlocked these heavier dead stars. So this wealth of black holes that are heavier than roughly about 20 times the mass of our own sun that we had no way of observing with electromagnetic radiation. And what's a little bit harder to see from this plot is that each one of these blue and orange dots are much, much farther away. So these red and yellow dots, so these are mostly galactic or maybe just past the edge of our own Milky Way galaxy, whereas some of these objects are many gigaparsecs away, so getting out into redshifts of about 1. They're very, very distant. And what can we really learn from these stellar graveyards? So we're now starting to get a lot of insight into what's out there and what's happening with the evolution of stars. So let's just take a quick tour of stars from formation in these vast dust clouds. And then depending on the size of that seed of dust, we'll either get a small star or a large star. And a small star like our sun is going to form a red giant, then a planetary nebula, and then eventually this white dwarf that will get cooler and cooler over time for millions and billions of years. So let's keep white dwarfs in mind when we talk about space gravitational waves and the LISA mission. And then larger stars, so stars more than about 8 to 20 times the mass of our sun. So these are also going to form these giant red giants, these supergiants. But then we expect these to go supernova. And depending on the mass of the star, it's either going to form a neutron star, so this dead core of neutrons that's so dense that they measure roughly about 1.3, 1.4 times the mass of our own sun, but they're only about a few kilometers in radius. So you could fit a neutron star essentially in the size of the Metro Vancouver area pretty easily. And they're so dense that a teaspoon of this neutron material is going to weigh more than Mount Everest. And then, of course, we have black holes, these collapsed regions of space-time where not even light can escape. And we do have reason to believe that these dark objects do have a really profound effect on their environment. So the evolution of galaxies and the formation and life of other stars. So what we're seeing here, so this is a simulation that includes stars. These are the light objects that are whizzing around. And then you also see this warping of space-time, this warped space-time field. And these are the dark objects, like the black holes and neutron stars that we're sensitive to with these LIGO and Virgo detectors. So looking at space-time, the sounds of space-time with our gravitational wave detectors is really teaching us a lot about the universe and what's out there that we can then compare with what we see with our telescopes. So where are we now? So the LIGO and Virgo detectors are currently upgrading. So what this means is that we expect to be back online with an improved sensitivity. So we'll be able to see farther out into space than ever before. And we currently expect to start the next observing run in March 2023. And we're also really happy that it seems like the Kagra detector in Japan will also be joining us. So we hope to be with a network of 4 detectors around the globe. And I also really love to mention that this effort is only made possible by well over 1,000 people. So there are hundreds and hundreds of us who are all working on very different aspects of building the detectors or analyzing the data. Communicating the science is also a really, really important job. And then this is not even including all of our wonderful astronomer partners who are looking at following up our candidate events and our alerts. So this is really a huge team effort. I have collaborators all over the world who speak many, many different languages and are from many different walks of life. And we all need to really work together to make this really exciting science happen. And then looking beyond our current detectors, so thinking about what else we can build. So we're at a period where it's pretty similar to looking up through a telescope for the very first time. There's so much room for growth with what we could do with a bit better technology. So what we're looking at here is the proposal to take a LIGO detector or a Virgo detector and then scale that from 3 or 4 kilometers to 20 or 40 kilometers. So we'd have these really enormous arms that would give us this reach into essentially all of the universe, the observable universe. So to give us some intuition for really what this might look like, so I've drawn a 40-kilometer detector with perpendicular arms to scale on a Google map. And you can see that if we end up building these, which I really hope that we do, they'll be on the scale of the distance between cities. So these would be absolutely enormous detectors, but it would be a great investment because what we would get is essentially everything. So here we are at the present day. So this is after galaxies and stars have had a really long time to evolve to what we currently see. And then this is looking back in time all the way back to the Big Bang. So just after the Dark Ages, where these first astronomical objects form. So this is called the cosmic dawn. And what we expect to be able to do with third generation or 3G detectors like the Cosmic Explorer is go from exploring this nearby recent universe. So for example, this dashed yellow line here. So this is the redshift of one of our recent detections, 1907-06. So this is at about a redshift of 1. And the limits that we expect our current generation of detectors to have is about roughly a redshift of 2. But if we were to build these great big detectors on the scale of tens of kilometers, we'd be seeing all the way back to the dawn of cosmic time. So we would capture absolutely every merger of stellar mass black holes, of neutron stars, and we'd be able to do this really incredible cosmology where we weave the distance information, that estimate that we get from gravitational waves, together with electromagnetic observations, to be able to measure the rate of expansion of the universe across redshifts. So really matching this data from the very early universe together with this recent universe to see this full picture of how the universe is evolving. And it also unlocks all of these really powerful methods, these tests of general relativity with this really incredible signal fidelity and precision, as well as using neutron stars and neutron stars mergers like laboratories for testing this very extremely dense matter in energies that are just impossible to reproduce on Earth. So this is all really exciting in terms of what we can do from Earth. And I also want to talk a little bit about what we can do from space. So let's take a look at where we are here. So thinking similarly to light and electromagnetic radiation, where we would have short wavelengths, and this would be something like gamma rays, and then long wavelengths would be something like radio waves. So we also see really different behavior for gravitational waves that have really different frequencies. If we think about that in terms of the period or how often we see the wave cresting, so at this very high frequency range, so here is where we'd have LIGO and Virgo and Cosmic Explorer on the surface of the Earth. So measuring things like supernovae and like stellar mass black holes that are crashing together. And then if we go to these lower frequencies, so these longer periods, what we're going to see is that we're going to need different tools. So actually turns out that the surface of the Earth is too noisy. It's moving around too much. There's a lot of sloshing around that happens, a lot of earthquakes. So this blinds us to those lower frequencies. So we'll actually have to go out to space to see what's happening with larger black holes. So black holes at the center of galaxies that are orbiting each other or eating smaller objects. So I'll tell you a little bit about this planned LISA mission, which is very exciting. And then we also have at the other end of the spectrum here, pulsar timing. So we'll talk a little bit about how pulsar timing works, but this is going to be showing us this really slow dance of supermassive black holes at the heart of merging galaxies that are orbiting each other on the scale of years to decades. And then finally, we might expect also to see a very early imprint of gravitational waves on the polarization of the cosmic microwave background itself. So this is also a really exciting set of research that's going on. And let's flip this around and put this together in terms of matching these detectors with these sources. So we're working backwards now here, where we've got periods, these lower periods on the right now and the longer periods on the left. And we see that, so LIGO and Virgo and Cosmic Explorer, they really have this unique space of sources, these exploding stars and rotating neutron stars on our own galaxy that we really only expect to be able to see with ground detectors. And then again, we're absolutely going to need to go off the surface of the Earth to a really quiet environment with something like the LISA detector in order to see something bigger. So these could be bigger black holes. This could also be supermassive black holes that are, again, consuming those smaller stars and smaller black holes. And then finally, we've got these supermassive black holes that are orbiting each other. We'll need to do something with even longer periods with that. So we'll talk a little bit about pulsar timing. And then we may also see these quantum fluctuations. So similar to the cosmic microwave background, we might expect the signature of gravitational waves from the very early universe may still be propagating, and we may still be able to sense this with our gravitational wave detectors that are planned. So let's jump into space interferometers and let's see what's happening with the LISA mission. So now instead of detectors that are 3 or 4 kilometers or 40 kilometers, now we're talking about millions of kilometers. So this LISA baseline is about 2.5 billion kilometers, and instead of an L shape, it would be a triangle. And this is going to allow us to sense gravitational waves coming from any given direction. So the planned mission for LISA, so LISA would be, again, just absolutely massive, so on the scale of a significant portion of the solar system. And the current plan is to have it lagging behind the Earth by roughly about 30 to 45 degrees. And its expected launch dates right now, so this is a mission that's currently being led by the European Space Agency. The expected launch dates is sometime in the early part of the next decade. So about 2032 is when we'd expect these 3 mirrors to launch, and then it would take about 18 months to get them in position in that triangle and ready to observe those gravitational waves. So this is a really, really exciting mission that we're all really looking forward to. It's going to give us, it would be sort of analogous to building the first radio telescope after only having optical observatories. So this is going to unlock some really extraordinary science. And then there's also, of course, pulsar timing. So this is using a galaxy scale array, a detector. So using these identified pulsars that are spread throughout our own Milky Way galaxy, and using these as very, very precise timers. So pulsars are extremely regular, especially some of these millisecond pulsars. And what this means is that we can look for correlated differences in timing between the pulsars in our galaxy to give us this very, very slow breathing of these low frequency gravitational waves that we expect to be generated by supermassive black holes that are orbiting each other. So there's a vast network of radio telescopes around the world that are working on this. So we recently lost Arecibo, of course, which was left a big hole in this international radio telescope effort. But there are a great deal of telescopes in North America and also Asia and Europe as well. And filling this hole in a really big way is a Canadian telescope. So this is a radio observatory called CHIME. That's pretty close to me here in British Columbia. And CHIME is very, very powerful. So it doesn't actually slew at all. So it's static and it observes as the Earth orbits, and it's able to measure this really precise information from pulsars on a really regular basis. So CHIME has been a wonderful tool for pulsar timing efforts, and it seems like that community is right on the cusp of making a detection of gravitational waves from these supermassive black holes. So that's really, really exciting. So there's quite a lot to look forward to, and we hope that you stay tuned. So we're going to have LIGO and Virgo coming online in 2023. Please pay attention to news from pulsar timing as they're analyzing more and more data. And then we've got LISA to look forward to in the next decade. So with that, I would be very happy to take any questions that you might have.
Thank you so much, Dr. McIver, for sharing this amazing look at the research into gravitational waves with us. We are now going over to check in with our RASC DDO coordinator, Quentin Wayrich, who's been monitoring the YouTube chat for questions. Quentin, over to you.
Hi, thank you, Dr. McIver. We currently don't have any questions from the YouTube chat. I would once again like to remind our viewers that if they have any questions at all for Dr. McIver, to please pose them now. That said, I have a couple questions of my own, if you don't mind me asking.
Please.
So first of all, I noticed that you would talk about like a redshift of 1 or 2, etc., when we're talking about these distant objects. So what exactly is that number and where does it come from?
That's such a good question. So we sort of glazed over the part where we think that the universe is expanding and has been expanding for a really, really long time. So a good way to think about this, I don't think I've actually had any ambulances go by. So I live pretty close to Vancouver General, so sometimes you can hear them in the background. But let's say that you're standing on a street corner and you hear an ambulance go by or an airplane go overhead. You can actually hear the pitch of that frequency that you're hearing change as it passes you. And what's happening is that whatever is emitting the sound is still emitting that sound at a constant frequency, but its position relative to you is causing you to hear it differently because it's actually changing the wavelength. So if it's coming towards you, it's compressing it just a little bit. And if it's going away from you, then it's stretching it out. So if something passes you, then you can expect to hear something like, woo. You might listen for that the next time you have a siren going nearby or an airplane. So something pretty similar here is happening where instead of this relative motion effect, where we've got this either compression or stretching happening, this is due to the expansion of the universe itself. So let's say I've got a star and the star is emitting light, and let's say it's emitting a hydrogen line. What's going to happen to the wavelength of that light coming from that star, if it's really, really far away from me, is that as it travels through the universe, it's going to get stretched out a little bit more as it passes through the universe. So let's say for every billion light years, it's going to get stretched out a little bit more as it travels towards me. So this is what redshift is. So I can actually get a sense of the era from which that star or that galaxy light was produced by how much something like that hydrogen line has shifted. So this is giving me a direct sense of how many times space has expanded. That's what this number is telling me. So I can think about, I can probably calculate directly that space-time has expanded by this redshift +1. So I'm able to infer both how far back in time I'm looking and then also how far that source is distant to me. That's a really great question.
Thank you. So it's related to the factor by which space has expanded since the light was emitted?
Exactly.
Okay, thank you. I have a question from Betty, actually, who asks, is there a distinction in the signature of the wave if it comes from the collision of two black holes or neutron stars?
That's such a good question. And the answer is yes, in a few different ways. So we were talking about how I can change my model based on the total mass of the system. So I can use general relativity to predict what the signal should look like, so the way that the wiggles in my signal should be wiggling, depending on what the mass of each one of those sources is. So I should be able to estimate what each individual source is. So I get more information about what we call the chirp mass, which is dictating essentially how quickly this frequency is evolving over time. This is related to the product of the masses and their sum mathematically. But yes, so essentially I'm going to get a change in the signature based on the masses, also how they're spinning. So if they're spinning quickly, if they're spinning relative to the orbital angular momentum of the system, or if they're maybe spinning opposite to that, that's also going to have an effect on the evolution of the signal. And then also if the objects have matter, so let's say if they're neutron stars or black holes, I'm going to see this, what we call this tidal distortion. I'm going to see some imprint of the matter being torn apart as those neutron stars are merging, whereas I don't expect to see that if I've just got two black holes. That's a wonderful question.
Okay, thank you. That's very informative. I have another question. I noticed that on your map of gravitational wave observatories that are on the surface of the Earth, there was a facility in Europe called GEO 600, but that wasn't mentioned in the talk. What is that?
That's a great question. So GEO 600, so this is the 600-meter prototype detector. It's an extremely important observatory in the development of these kilometer scale detectors. So they have prototyped light squeezing, they've prototyped a few other really key technologies that we employ in LIGO, Virgo, and Kagra, but the observatory arms are not long enough for them to be as sensitive. So we don't normally analyze the data from GEO 600, even though it is such a pivotal observatory, and that's completely enabled all the results that I've been able to share with you.
Okay. Well, I have another question, if that's okay.
Sure, please go ahead.
Do you think that gravitational wave astronomy will someday become sophisticated enough for us to map out the mass distribution in the galaxy? Could we use these techniques to find dark matter, basically?
That's a really good question. So something that we haven't mentioned explicitly is that we're only going to see gravitational radiation where we've got some asymmetric distribution of mass that's changing. So we need something that's accelerating, and we need it to be asymmetric. So for example, if I have a perfectly spherical neutron star and it's spinning, then I don't expect to see anything. But let's say I have, through my modeling of a neutron star structure, expect that the crust is going to be able to support some distortion, maybe a bump or a little mountain, even on the scale of millimeters or centimeters. Now when I look at that star that's spinning, I'm going to get a sinusoidal gravitational wave. So we're going to need to be looking for, or we're going to be limited to sources that are dense, that are compact, and that are accelerating in some way. So if there's some exotic dark matter candidate that is interacting in some way, let's say maybe there's a cloud of dark matter around a black hole as it's merging with another black hole, that might be a way for us to probe dark matter models. But in terms of mapping this really disparate spread of dark matter, it's going to be really challenging for gravitational waves to do this.
Okay, Betty has another question. I had wondered about the James Webb Space Telescope, if it might be a factor in conjunction with the discovery of gravitational waves.
We are really excited about James Webb. Yes, absolutely. So what we mentioned a little bit is that there are some sources, so especially if you have two neutron stars merging together, or maybe a neutron star and a small black hole that merge together, you expect this to produce some kind of a counterpart light signature. And James Webb would allow us to really explore this incredible richness of data with such a source that's discovered. So it would probably take something more like LSST and Vera Rubin in order to find it quickly. So James Webb is probably something that you don't want to spend a lot of time pointing to a lot of different candidates. But once you've found the source, I think it's going to be a really incredible complement to gravitational waves to get a very rich picture of data from that near infrared wavelength.
I think we're all excited about James Webb. James Webb is huge.
Yeah, absolutely.
I have one more question left. Still
Sure.
no questions from chat. I would once again like to remind the viewers, if they have any questions, they should pose them now. But I wanted to ask, how did you get interested in astronomy?
That's a really good question. So for me, I'd sort of been casually interested when I was younger. I'd read some books on astronomy, but I had a really fantastic teacher when I was in undergraduate who encouraged the class to get involved with research. And I went to knock on his door and I said, "What are we doing? What's the research?" And he introduced me to LIGO and gravitational waves. I thought, well, that's pretty wild, and I've been on the train ever since.
Thank you so much, Dr. McIver. This was such a fascinating topic. This really is like the opening of a new frontier in astronomy, and I can't wait to see where we go over the next couple decades. So thank you very much.
My pleasure.
Thank you, Quentin, for relaying all of those awesome questions. And thank you so much, Dr. McIver, for answering them in such detail. We have learned quite a lot tonight about gravitational waves.